In section 2.4, our objective is to take the derivative of composite functions. First, let's start with taking the derivative of y with respect to x for this. Now, these are not in your printed notes. I want you to just sit back and watch and try to answer before I write it down. So I'm taking the derivative of y with respect to x. That's right, 4x cubed. Now I'm taking the derivative of u with respect to x. So that's du dx. Well, I said take the derivative of u with respect to x. I see u, I see x, so it's no different than above. Now I'm saying take the derivative of y with respect to u. Well, again, I see the variables y, I see the variable u, so the derivative of y with respect to u, 4u to the fourth. What about this one? The derivative of y with respect to x. Well, this time I have something else besides x to the fourth. So let's think of this like u. So let's think of it like it's y equals u to the fourth. This is a composite function where there's a function, 2x plus 1, inside another function, u to the fourth. So to take the derivative of a composite function, we have to think of first doing the derivative of the outer function, or rather first taking the derivative of y with respect to u. However, I want the derivative of y with respect to x. So how do I get rid of the u? Well, just thinking of this like it's division, if I want to get rid of du on the bottom, I multiply by a du so they cancel out. And if I want a dx on the bottom, I divide by dx. So I'm multiplying dy du by du dx. Those multiplied give me dy dx. So here's what this means. The derivative of y with respect to u means the derivative of this. This expression is 4u cubed. The derivative of u with respect to x, well, if u is this inside function, u is the inside function, u is 2x plus 1, the derivative of it is 2. Well, put those things together, I'm multiplying the derivative of the outer function times the derivative of the inner function. But what did we say u really represents is 2x plus 1. So altogether, I can say this is 4u cubed times 2, or 4 2x plus 1 cubed times 2. Sure, we can simplify that to 8 times 2x plus 1 cubed. So to summarize, we took the derivative of the outside, take the 4, multiply it out in the front, 4 multiplied out in the front, reduced 1 from the exponent. Then the inside took its derivative times 2. Then we simplified. This is called the chain rule.
Chain, chain, chain. Chain, chain, chain.
Now we can go down.
Chain, chain, chain.
Here's another example.
Chain, chain, chain. Chain, chain, chain. Chain, chain, chain of food. For 5 long years.
Now I'm going to let you jam out pretty soon. Let me just explain what I did here. The derivative of the outside, take the 4, bring it out in front, 4 out in front, reduce the exponent by 1. Notice the inside stays the same. Then multiply by the derivative of the inside. Now, did you bring your M&Ms with you? Because this is where you need them. This is called the chain rule, and it's really helpful to understand the chain rule with the M&Ms. You've got an outer function, the something to the fourth. So something, something to the fourth. We do the derivative of the outer function. Now, if you really love chocolate, you're going to savor your M&Ms. So first, we're going to just eat the shell, just the outer part of the function. We're going to eat the outer part, which is eating the shell. Go ahead and take out an M&M and just suck on it a little while. You're only eating the shell. Taking the derivative is like eating in this analogy. Once we do the outer part, which is the exponent out in front, reduce the exponent by 1, we're not touching the inside at all. Then we eat the shell. Now we get to the good stuff. Now we get to the chocolate. Now we can eat that chocolate. So we take the derivative, or we eat the inside, and the inner is eating the chocolate. We eat the chocolate. That's called the chain rule.
Chain, 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 chain of food. For 5 long years, I thought you were my man, but I found out I'm just a link in your chain.
We'll come back. We'll jam out soon in a little bit. Please make sure you're making a note that we are differentiating composite functions when we are doing the chain rule. This is a way to look at it where we say first we take the derivative of the outside, so the derivative of the outside, or we eat the shell of our M&M. Then we take the derivative of the inside, or we eat the chocolate. Another way to look at a composite function is like this. F of another function, g of x, a function inside a function. I want to take the derivative of f of g of x. Well, let's talk about it as outer function and inner function. First, we eat the shell. Here's the shell, f of something. So the outer, the outside first, f prime of that something. We don't touch that inside. It stays the same while we eat the shell. Then the inside, which is represented by our u in this scenario, is g of x. So now I'm multiplying by the derivative of g prime of x. So I'm multiplying by the derivative of the inside, or now I'm eating the chocolate. So go ahead, grab your M&Ms, savor them. We're going to go through a bunch of examples. Maybe you pause the video at times and try some on your own. Let's do a couple maybe together first. Looking at number 1, we know it's a composite function because I have stuff to the 10th. So all of this to the 10th creates my outer function. The inside I don't touch yet. So as I do dy dx, first I'm doing the derivative of the outside, move the 10 out in front, leave the inside the same. Take 1 away from the exponent, there I've eaten the shell. Now I get to eat the chocolate, and the chocolate is the inside, and the derivative is eating. So the derivative of x cubed plus 7, 3x squared plus 0. Leave it like this. This is a good answer. Or simplify a little bit. 3 times 10 is 30. 30x squared in the front of x cubed plus 7 to the 9th. You want to try this one on your own? Come back. Maybe first you rewrite it like this. Give it a shot. See how you do. Let's do the outer part first. The outer part is all of this to the 1/2. 1/2 out in front. Leave the inside the same as we subtract 1 from the exponent and then multiply by the derivative of the inside, 3x squared. This is a fine derivative. Leave it like this or do some rewriting. 3x squared over 2, because it's 1/2. This part has a negative exponent, so put it in the denominator, rewrite it with the radical. I put the next two side by side because they look very similar but are very different. This one is saying sine x function, all of it is to the 5th. This one is saying the sine of x to the 5th. The inside functions are different here. This one, the chocolate, the inside is sine of x. This one, the chocolate, the inside is x to the fifth. If we're doing the outside first, that's the power function, is stuff to the fifth. So first, as I take dy dx, I do the outside, so bring the 5 out in front. Sine of x stays the same to the fourth. Now I do the inside. The derivative of sine x is cosine x. I have a derivative. I can leave it like that. Or you rewrite it with fewer parentheses. 4 can goes here. That's a shortcut for saying sine of x to the fourth times the cosine of x. This one, the outside, this time is the sine function. Sine is the outside, so that's the part that gets changed. So as I do my derivative, dy dx, I'm taking the derivative of sine of x, which is cosine of x, but it's cosine of, not x, x to the fifth. The inside is staying the same. Once I did the derivative of the inside, now I can do the derivative, or sorry, the derivative of the outside. Now I can do the derivative of the inside. There it is. Perhaps you want to rewrite it, put the 5x to the fourth here. Otherwise, you really do need parentheses like this. 5x to the fourth cosine of x to the fifth. You want to try a couple on your own? I'm going to work through it while I jam out to Chain of Fools.
Oh, you got me where you want me. I ain't nothing but your fool. You treat me mean. Oh, you treat me cruel. Chain, 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 chain of fools. Every chain has got a weak link. I might be weak time, but I'll give you strength. Oh, you told me to leave you alone. My father said, "Come on home." My doctor said, "Take it easy." Oh, but your loving is much too strong. I'm headed to your chain, chain, chain. 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 Your chain of fools. Oh, one of these mornings, the chain is gonna break. But up until then, yeah, I'm gonna take all I can take. Oh, yeah. Chain, chain, chain. Chain, chain.
Okay, now you need to break out the next M&Ms. Break out your peanut M&Ms because this is double chain. What does double chain mean? Let's look at it. Another way to write this. Sine of 8x. But instead of the little 5 here, what that means is all of that is to the fifth. So we've got the outermost function is stuff to the fifth. That's our shell. So first, let's take this one step at a time. dy dx. First, I deal with my shell. Bring the 5 in the front. Everything inside stays the same. We're just sucking on the shell. We're just doing the outer derivative. All of that is the shell. What do you get through after the shell? You get to the chocolate. Well, the chocolate is what's inside the shell, all of that stuff that's inside. So sine is the next inside. That's what we take the derivative of first. Well, next. Derivative of sine is cosine, while the 8x doesn't get touched. Remember, you're eating a peanut M&M, so as you savor this, as you suck on this, all you're eating right now is the chocolate. After you get through the chocolate, that's when you get to the peanut. The peanut is 8x. What's the derivative of 8x? 8. That's the peanut. I have a derivative, but perhaps we simplify it a little bit. 8 times 5, 40. Sine, instead of with the 4 outside, to the fourth of 8x, and cosine of 8x. I'm going to work through the next double chain. If you want to pause the video, give it a shot, or you can jam out with me and then check your work.
Chain, 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 chain of food. For 5 long years, I thought you were my man, but I found out I'm just a link in your chain. Oh, you got me where you want me. I ain't nothing but your fool. You treat me mean. Oh, you treat me cruel. Chain, 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 chain of food. Every chain has got a weak link.
Negative exponent, 2.
I might be weak, child, but I'll give you strength. Oh, you told me to leave you alone. My father said, come on
1
home.
minus 1f.
My doctor said, take it easy. Oh, but your loving is much too strong. I'm headed to your chain, chain.
And 1/2 exponent becomes, it became 1/2 because this was to the first, this was 1/2. 1 minus 1/2 becomes 1/2 in the top. So that's where I'm getting my secant of x to the 5th plus 3x. This one, tangent x to the 5th plus 3x. Now, all the rest, just more examples. I encourage you to give them a shot, to try them, and keep practicing. Maybe pause the video, maybe do it along with me. I'm going to work through them, and I'm going to jam out to some chain of fools here and there. First one, I see it's a quotient. I could use quotient rule, well, 9th one rather, but if I bring this up, 4x squared plus 6x minus 7 to the negative 3, now it's not a quotient anymore, just a chain rule. So again, as we work through, outer function first, negative 3 out in front, all the inside stays the same. Subtract 1 from the exponent is negative 4. Leave it like this or rewrite it. The next one, number 10, very much a quotient, and absolutely quotient can be used, but when I encounter problems like these where the top doesn't have an x, I always rewrite it so it's not a quotient, because I think chain rule is faster than quotient rule if I have a choice. So rewriting it, I bring the negative 1 out in the front, subtract 1 from the exponent, keep the inside the same, and then multiply by the derivative of the inside. There's our chocolate. This makes negative 10x over 5x squared plus 6 squared. Now wait just a minute there, lady. What about the inner function? What about the chocolate? Don't skip the best part. So here's our inner function. We need the derivative of that. Back to number 9 is where I'm looking. The derivative of the chocolate, 8x plus 6. So let's go ahead and put that here, 8x plus 6. Now we can say we've done it. Can't forget about that chocolate. Next ones I put side by side because they look very similar, yet they're very different. This one is a composite. This is the cotangent of the sine of x versus this one is a product. This one is the cotangent of x times the sine of x. We do them differently. Here, I have to do the chain rule. Composite means do the chain rule. So first, I do the outer function. The derivative of cotangent is negative cosecant squared. The inside stays the same. Now, I can eat the chocolate. Derivative of sine is cosine of x. Rearrange it if you want to, or don't. It's the same, but you probably should put brackets here to make it a little bit more correct. This one, product, means we need product rule. So think about your product rule. One times the derivative of the other plus the other times the derivative of the one. And let's roll from there. Two of them are f and g. So I'm going to take one of the functions, cotangent x, times the derivative of the other function. Sine of x turns into cosine of x plus sine of x times f prime, the derivative cotangent, negative cosecant squared of x. Leave it like that, or maybe you simplify it a little bit. So we could say cotangent is cosine over sine, but does that really simplify anything here? Not really, so maybe we just write them next to each other. Minus, to get rid of some of the parentheses, sine of x times, well, cosecant squared is 1 over sine squared, so I could write it like that, or just get rid of the parentheses. Lots of versions when it's a trig function. Let's try a couple others, and notice how similar they look, yet are very different. This one is the cosine of 2x to the fifth. I'm going to rewrite it. Cosine of 2x to the fifth. You won't see parentheses, but it implies parentheses around that. This one, the parentheses is around cosine 2. This is just a coefficient, a constant multiple. Cosine of 2 is a number. It doesn't have an x in there, so it's not a product. And it's not the cosine of something that has an x in there. So when I take the derivative, or get k prime of x, I leave that constant multiple out in the front while I do the derivative of that little guy next to him, 5x to the fourth. That's it. This one is different. This one is the chain rule because it's composite. Let's jam out while we do this one. Let's practice a couple other ones I got from an AP test. And again, these are just some more of the same practice, so you can either practice on your own or listen to me. First, I notice that I have a product of two functions, call it f and g. This one, I have to think first, use the product rule. dy dx. dy dx is using the product rule, fg prime plus gf prime. F is the first one, x squared. G prime is the derivative of the second. Now, as I do the derivative of that one, that is a composite. So I've got my outer function is sine. The derivative is cosine. Then there's the inside of it, 2x. Its derivative is 2. Let's do the rest of our product rule. G is sine of 2x, and f prime is 2x. That's my derivative. I can stop there or simplify it a little bit like 2x, 2x. I can factor out a 2x from both. I'm left with an x and a cosine of 2x from the first term. And taking out 2x, I'm left with a sine of 2x from the second one. This one, also a product, f and g. So again, as I do the derivative, or g prime of x, I probably don't want to call these f and g. I just realized because my big function is called g. So maybe we practice with different letters, u and v. So uv prime plus vu prime. Doesn't matter what we call them, it's one of them with the derivative of the other. One of the other one with the derivative of the one, and we're adding them together. So u is the first one. V prime, well, that's a composite. This to the 1/2 instead of square root. So 1/2, inside stays the same, subtract 1 from the exponent. Then do the derivative of the inside, 2. Then simplify because we have a derivative, but we can make it simpler, such as 1/2 times 2 and negative exponents, put it back in the denominator. This is prettier. Now, of course, we have to finish our product rule. This is just u and v prime. So plus the v is square root of 2x minus 3, and the u prime, the derivative of x, is 1. So now we can simplify this to make it a little bit better. This makes x over, because of the negative exponent, square root of 2x minus 3, plus square root of 2x minus 3. Again, this is a derivative, this is fine. However, I do want to get a common denominator because in a multiple choice question, that's what I'll usually see. So multiply by 2x, square root of 2x minus 3, and then that makes this part just 2x minus 3, and I can combine like terms. So here we get x plus 2x for 3x minus 3 over the common denominator. That was fun. Finally, a question that asks a little bit differently how to find the derivative. Find the equation of the line tangent. Well, remember what we need for an equation of a line. We need a point, we have that, and we need a slope. So let's find the slope. What is slope? Derivative. Let's look at this function. I see a product inside another function, but I can distribute in there. So let's really call f of x, x minus 2x squared to the third. That way it's just a composite. So I have my outer function stuffed to the third. 3 in the front, x minus 2x squared stays the same, reduce the exponent by 1. That's the first part. Then the inside, the chocolate, is x minus 2x squared, the derivative 1 minus 4x. Now remember, our goal for finding the derivative is finding the slope. So now we're going to plug in, without simplifying, our x value of 1 into the derivative. 3 times 1 minus, plug in 1 there, that makes 2. 1 minus 2 squared, 1 minus, plug in 1 there, 1 minus 4. Negative 1 squared, negative 3, looks like we're getting negative 9. That's our slope. I'm going to uncircle because I don't want anyone to think that's my final answer. That's our slope. We need the equation of a line. Y minus the y coordinate equals the slope, x minus the x coordinate. We're done here, or if you prefer, get rid of the double negatives, and it's a little bit prettier. Thanks for playing.
Change, change, change.